All right, chapter 5 involves the natural logarithm function and exponential functions. And in section 1, we're going to be working with the natural log function and taking its derivative. This entire section is about the derivative of the natural log function. And then section 2 is the integral. So here we go. The general power rule for integration, as we have learned from the last chapter, is this. If I have x to the nth power, I can integrate it using x to the n plus 1 divided by n plus 1. But the problem is this guy right here. What happens when we have n equals -1? Yeah, so we were not able to integrate 1 over x. Because when you rewrite that, you get the integral of x to the -1, and then n is -1. So you wind up with -1 plus 1, which is 0. So x to the 0 divided by 0, which we can't ever do. So we had a problem. We could not integrate that thing. And we avoided it the entire chapter 4. Just kind of ignored it. Well, now we're not ignoring it anymore. It turns out we can integrate that situation. The result is a logarithmic function. Here's your definition right here of the natural log of x in terms of integration. If I have 1 over t dt and I integrate from 1 to x, so what rule is this right here? Or what law that I'm using? Or theorem? It shouldn't take more than 1 second to figure out this theorem because it is the second fundamental theorem of calculus. This guy right here allows me to switch variables, and when I integrate, I wind up with this. So the definition of the natural log of x is going to be this guy. But we're dealing with differentiation in this section. So that means if I take the derivative of the natural log of x, what do I wind up with? If I take the derivative of the natural log of x, I wind up with that, 1 over x. Okay? So that's where we're headed. The domain of the natural log of x is positive numbers only. But the range is that bold R means all real numbers. And we'll take a look at the graph of the natural log of x here in a little bit, and you'll see that the domain is only the positives. So the general rules for the natural log are similar to the general rules for log, and that's why we reviewed them. So this should make sense because the natural log is just a logarithm with a special base. And we just call it the natural log instead. So the natural log of 1 is 0. We talked about that one. The natural log of something to an exponent, I can take that exponent and write it out front, and then I have that exponent times the natural log of that something. If I have two things being multiplied together and I'm taking the natural log of that, I can split them up using addition. The natural log of that first thing plus the natural log of that second thing. And finally, if I'm dividing something and I'm taking the natural log of it, I can split that up using subtraction this time. The natural log of the numerator minus the natural log of the denominator. All right, this is some practice problems. I have all of the little rules off to the left, and we just want to expand these. This is practice from problems that you probably did back in pre-calculus. The natural log of 10 over 9 would become what? Natural log of 10 minus natural log of 9. Now, I could actually go slightly farther here, and sometimes the book will do this as their answers. Because of the fact that 9 is a perfect square, I can rewrite natural log of 9 as the natural log of 3 squared. It's possible that the book would do this, natural log of 10 minus, and now use that 2 out front, 2 natural log 3. So just be aware that that can happen. So when you're looking in the back and you see an answer that doesn't quite match, look for exponents that they shifted down, that were embedded within perfect squares or something like that. It doesn't always happen, but I know there's a couple problems where that does happen. All right, natural log of this guy, what should we do? Rewrite to what? Okay, now that I've done that, what can I do? Oh, sorry. Yeah, I think you did. It's totally your fault. Now what? So the 1/2 comes down, natural log 3x plus 2. Now what? Yeah, that's as far as you can go. I see a common mistake where people remember that they can split up natural logs by creating addition. And it's kind of natural to see that addition right there and think that, oh, I need to split that up. And that's a common mistake. That's not the case. We do have multiplication going on right here, but it's not 3 times this whole thing. So we can't split that up either. This is the answer. How about the next one? Yeah. Take care of the obvious thing first. So we have natural log 6x minus natural log 5. Is there anything else I can do? Right. Now that I've done this, this is just multiplication of 2 things. So I have what? Good. Okay. So I guess those were the easy ones. Now let's do the last one. What are you trying to take care of first? Take out the division first. Now as you're going, you were already moving the exponent down, and that's fine. We're going to have to rewrite this guy, but we can move that exponent down right off the bat. That's cool. So we have what? See, that's a good question. I think that's a cube root. Don't do too much at once. One-third. Okay, and then all of that has the natural log on it. So I'm going to show that by doing that. Yeah. Is there anything more to do with this guy? No. So we have 2 natural log x squared plus 3, then minus what? Okay, be careful because this is an x times this. So if you bring the 1/3 down now, then what you're saying is that that was actually all being cube rooted, which was not the case. So we have to split this first, then we can bring the 1/3 down. So we have, since this is minus right now, we need to include parentheses here. Close those parentheses. Can we go any farther? Yeah, distribute the negative sign in. This can't be touched anymore. So we just have 2 natural log x squared plus 3 minus natural log x minus 1/3 natural log x squared plus 1. And that's it. Graphing natural log by hand. We could easily graph natural log on a calculator, but let's figure this thing out by hand because it's a little bit more revealing if we do that. So we want to generate a slope field for dy over dx equals 1 over x because I know that if I integrate 1 over x, I get natural log x. By using the differential equation here, this format, I can generate the slope field, which would show me how this function looks anywhere for all possible functions. So to do that, this is like the first time in class that we've done this, even though on homework we're kind of seeing a couple slope fields here and there. To do that, what I need to do is plug in values for x. Since in this equation right here, all I have is values of x. If there was a y here also, then I'd have to pick ordered pairs. But since I don't have a y in this part, all I need to do is pick values of x. When I do that, I'm going to get a dy over dx as my answers. What is dy over dx? No, what is it? Like In general, what is dy over dx? Give me one word. More importantly, it's the slope. So what you're doing is you're picking values, and we'll pick 0, 1, 2, 3, and 4, maybe 5, we'll see. What you're doing is you're picking values of x, or if we had ordered pairs to plug in, we'd plug in ordered pairs, and we're calculating the slope at each of those ordered pairs, or in this case, just anywhere that x is 0, anywhere that x is 1, anywhere that x is 2. Once you have all those slopes, then you've created a slope field. That's the whole point. So here we go. If I plug 0 into this equation, what do I get? Undefined. The world just exploded. If I plug 1 in, what do I get? 1. And if I plug 2 in, I get 1/2. If I plug 3 in, I get, yeah, and then, okay. Yeah, so our slope is getting less and less, but each time our slope is positive. Okay? All right. Good, it's always increasing. I have that down here. So we'll talk about that in a little bit. For x is 0, when x is 0, we're on the y-axis, and our slope is undefined, which means that it would look like what? All lines are straight. Vertical. So our slope here is vertical. Each of these little tick marks is just showing what my slope is. Now for my x value of 1, that means here. Anywhere when x is 1, my slope is 1. So I'm going to try to draw in a slope of 1 all along when x is 1. Then when x is 2, I have a slope of 1/2. So when x is 2, that's all along here. I have a slope of 1/2. So I'm going to try to draw a slope of 1/2 on here. And then a slope of 1/3 when x is 3. So a slope of 1/3 would be like up 1 or right 3. So I'm starting here, and I'm kind of tracing my hand over so that I can try to get that slope of 1/3 in there. That was too high. And then 1/4, again, up 1, right 4 is the slope of 1/4. So I'm trying to go on a line path kind of like this. If you have a ruler or something straight, this becomes a lot easier to draw in a slope field. And then 1/5, now we're getting very flat. And the next one would be 1/6. So I'm just going to keep going, really trying to go as flat as I can. It's not the easiest thing on this board. Okay, not that I'm trying to make excuses, but that's your slope field. So now all I need to do is pick, like if I was asked to generate the graph that goes through, let's say, 2, -1, then this slope field kind of dictates what that thing's going to look like. You can kind of see how that would sort of do something like that. I'm just trying to match up the slopes as I go. Okay, you kind of see that? All right. So the result is, no matter what happens, as I go closer and closer here, what's going to happen to my natural log graph? It's going to take off. Is it ever going to cross over that spot? No. And that's why in the last page or whatever we said that the natural log function is always positive. The domain is positive numbers. But will I ever stop increasing here? If my slope is getting smaller and smaller and smaller. As x goes to infinity, eventually I'll become horizontal. But I can shift this up and down in any old way that I want. Like I just happen to pick this number here. I could pick this number here, or I could pick 2,000 or -871. That's why the range is all real numbers. Okay? All right, the natural log function is always increasing. We can kind of see that. even though towards the end it will become almost horizontal. Always increasing or always decreasing, that vocab word monotonic. I don't know if it's monotonic or monotonic, but I call it monotonic. It's a good vocab word to use, especially on the AP exam if you're given a function that's always increasing or always decreasing. It's continuous, even though it doesn't extend forever this way, it's still a continuous function, and it's always concave down based on our slope field here. So that's why slope fields are kind of nice. It's a good idea to know how to generate those and look at them and analyze them. Okay, using a calculator to evaluate. There's times, not all the time, but there's times when we'll ask you to evaluate these. So just use any calculator that has the natural logarithm function on it, and you can come up with these answers. There's no need to change modes or anything like that, I think. So just type in what you have. Give me 3 decimal places in your answer. So you'll look at the 4th decimal place and decide if you have to round up or down. Take a minute to familiarize. Well, yeah, you know how to do that. So what is the natural log of 2?
0.693.
Yeah? What is the natural log of 32?
3.46.
And what is the natural log of 0.1? Negative 2.303. Okay? Is everybody good with all those? Why is it negative? Let me go back to the graph. 0.1 is like right here. And granted, I picked this as my original here, but if you were to graph, and we will, when we graph the natural log function, we'll see this behavior here. And it turns out that this graph actually normally lives up here. So by the time you get to here, the graph has gone negative. Okay? Remember that x values in the natural log can't be negative, but y values can be. So there's our graph, and you can see that that's kind of what I was referring to here. This thing takes off. This will eventually become a little bit more horizontal as it goes. But over here, like after between 0 and 1, this thing is negative. So let me let's do a couple more. What's the natural log of negative 2? You can't, but type it into your calculator and see what it gives you. Yeah, so undefined on that one. Error. How about natural log of 0?
Undefined.
Did they say undefined on that one?
Yeah.
Okay. All right. How about natural log of 1? 0. So when x is 1, that's when the graph crosses and becomes negative. We'll talk about natural log of 1 here in a little bit and why it's 0. But that's the graph. That's what we're working with. Oh, why is it 0?
Because natural log is log base e.
Okay.
And so the other one would be something like rewrote that next one would be e.
So what you have is log base e1 equals 0, right? So if you rewrote that in exponential form, what would you have? Anything to the 0 is? Yes. So that's why natural log 1 is equal to 0, logically. We need to review our derivative situations. What is the product rule? F prime G plus G prime F. And the quotient rule? Good? Yes. Thank you. And the chain rule in our short format? F prime U times U prime. That's the chain rule. And then one more thing, natural log of E is equal to 1 along the same logic as The natural log of 1 is equal to 0. Why is the natural log of e equal to 1?
The log is
Of what?
e.
So that's what we have. Why? E to the 1 equals e. So that's why this one is true also. It turns out that the natural log and e are inverses of each other. They undo each other. We're going to be working with that property a lot in this chapter, but you might as well know it now. Kind of like squaring and square rooting undo each other. Natural log and e undo each other as well. Okay. Time for some calculus. The derivative of the natural log of x we already talked about based on the definition that I gave you in the beginning. The derivative of the natural log of x is 1 over x. Remember that x has to be positive in that case. If I apply the chain rule to that, so now I just have the natural log of some function here, so that becomes the natural log of that function, u. Then if I use the chain rule, I get the 1 over u like I would get 1 over x here, but then I have to multiply on the u prime. So it's still the chain rule. A way to rewrite this is du over dx is u prime. 1 over u is just 1 over u. So what this actually is 1 over u times u prime, which means I can rewrite that as u prime over u. So it's another way that these answers can be written. The trick is recognizing that it's a chain rule, which you've had lots of practice with in the first place, so that shouldn't be too tough. But then applying the fact that you need the 1 over u and then times the u prime. So it just takes a little bit of practice. We have a bunch of practice problems sitting here. They use the properties that we've talked about for differentiation. So be ready at any time to have to use any one of them or a combination thereof. So with this one, what should I probably do? This is a chain rule. U equals what? 2x. So therefore u prime equals 2. Now notice that we're not integrating here. I'm not writing this as du equals 2 dx. I'm writing it by taking the derivative u prime so that it matches what I have over here. So now what I have is d over dx of the natural log of u. It basically fits that pattern exactly right there. So I get 1 over 2x. 1 over u, but u is 2x. Times u prime, which is 2. So that gives me 2 over 2x, which reduces to 1 over x. Should I include a plus c here? No? Why not? Yeah, we're taking the derivative. All right, how about the next one?
U equals x squared plus 1. U prime is just 2x. And we do that.
All right.
We get 1 over, well, d over dx.
So now I have the derivative of the natural log of u, which I probably don't need to write down.
So 1 over x squared plus 1 times dx.
Okay, which is 2x over x squared plus 1. And that's it. That's the answer. So I want to point out this look right here, the u prime over u. If I call u this, then my numerator is 2x. And then my u is my denominator, x squared plus 1. So you can, it's possible, to go from having to do all of this to going straight from here to here. It's possible. Don't do it right away until you start to really understand the math that's going on here. But once you understand the math, you can go straight to that. How about this one? Yeah, that's the product rule. So what do we have? All right, so f prime is what? It's 1. F prime. Take the derivative of x, you get 1. Times the original g, which is natural log x.
Plus g prime is 1 over x.
That's 1 over x.
Times x, which is
So that's 1, and we get plus 1. No, don't even try to do that, because then people are going to start writing that down. All right, the last one. Chain rule, good. What do I write? Squared. General power rule there. So the 3 comes down. What's inside stays the same. Decay the exponent by 1 times the derivative of what's inside, which is 1 over x. So there's your answer. I could have written the times 1 over x here, but then I'd have to simplify it. So there's my answer. Okay? Can't simplify any farther than that.